All right, one more video from 4.3 dealing with logarithms. So thinking back to 4.1 when we were talking about exponential functions, we talked about how e, which just is a constant that's roughly equal to 2.7, is the perfect, in some sense, base for an exponential function. And why it's so perfect doesn't really get made clear until you get into a calculus class, so I didn't waste too much time. I just hope that you trust me that this serves as a really nice base for exponential functions. So think about if I had the function f of x equals e to the x power. So this is an exponential function and playing the role of a as a 1 and playing the role of b as this e right here. What if I was interested in figuring out when the output of this function was, I don't know, 20, for example? What if I was interested in solving this equation when f of x equals 20? Well, what I'm trying to figure out here is when is the output of this function e to the x power equal to 20? I want to solve this equation for x. But how do I solve this equation for x? How do I get this x all by itself? Well, a few chapters ago, you'd be like, I have no idea. I don't know what power you raise e up to make it equal to 20. But now that I know logarithms, I can rewrite this equation. I can say that the log base e, because the base here is an e, of 20, the number over on the other side, is equal to x. If I wanted to solve this equation for x, all I would have to do is transform this from exponential notation to logarithmic notation. The solution to this equation is the log base e of 20. And I know that doesn't feel like a solution, that feels like there's more work to be done there, but we're done at this point. This represents a number, and that number is the solution to this equation. It's not a nice whole number. I can't take this irrational number and raise it to, I don't know, like the third or the fourth power and get 20 as my answer. It's some decimal, but the way I can express that decimal is the log base e of 20. And this might seem like a really obscure example, but I want to make the argument that this isn't as obscure as you might think. Because e is a really common base that we're used in exponential functions, and e is this irrational number, often when I have to solve an equation where the output of this function is equal to some number, like the number 20, what I'm going to end up with as the answer for x will be some ugly looking decimal. So the way I will represent that number is with the log base e. What I'm trying to say is because e is a great base for exponential functions, you often need to know the log base e of a number. In fact, it's so common that you need to know the log base e that there's special notation to write this. Anytime you want the log base e, you can rewrite that as ln. What ln stands for is natural log. And you're like, wait, shouldn't that be NL? Yeah, but it's French and it's like logarithm naturel or something. I obviously don't speak French. The point is just that ln stands for natural log, and the natural log just means the log base e. Because the log base e is so common, we have shorthand for it. Instead of writing 4 characters, L, O, G, and an E, we can just write 2 characters, an L and an N, and you, the student, are supposed to recognize that ln just means log base e. So if somebody asked you what the natural log of 1 over e, for example, were equal to, at first it looks really, really confusing, but if you can remember that ln, the natural log, just means the log base e, really this question is just asking you what's the log base e of 1 over e. And maybe you could figure this out just the way it's written. If you can't figure out the way it's written, what you can do is you can set it equal to x and then convert it from logarithmic form to exponential form. I take this base, e, and I raise it up to the x power, the number over on the other side, and what I want to do is set that equal to this 1 over e. I want to ask myself the question, what power must I raise e up to, this base here, to make it equal to 1 over e? Well, e to the negative 1 power is equal to 1 over e. Therefore, the natural log of 1 over e is just equal to negative 1. Another base that's fairly common when we're dealing with exponential functions is base 10. So here's an exponential function. Again, a is the implied 1 in this case, and b is equal to 10. G of x equals 10 to the x power. You might be interested in solving, I don't know, g of x equals a million. And you're like, a million without a calculator? That's super hard. I'm not used to seeing numbers that big in this class, but it's really not that bad. All this is saying is g of x is 10 to the x power, so I want to know what number x will make 10 to the x equal to 1 million. Tens work out really nicely. Right? 10 times 10 is 100. 10 times 10 times 10 is 1,000. When you're multiplying by tens, because we have this base 10 system that our number system is based on, it's really easy to take powers of 10. If I want to figure out what power I have to raise 10 up to get a million, all I got to do is come over here and count zeros. There's 6 zeros over here, so 10 to the 6th power is equal to 1 million. The solution to this equation is that x would be equal to 6. Note we didn't use logs at all there, but we could have used logs. When we were solving this equation, 10 to the x equals a million, instead of just figuring out what x could be equal to, We could have switched this from exponential to logarithmic form, in which case we would have said that the log base 10 of 1 million is what x is equal to. And I realize that wouldn't have been necessary in this case because 10 to the 6 just equals a million. But what if this weren't a million? What if this were 1,135,000? Something close to a million, but not exactly a million. We might want to be able to express that answer as a decimal. You wouldn't be able to figure out what that decimal is equal to just by looking at these equations, but you could express that using logs. The point that I'm trying to make with this example in blue was supposed to be kind of parallel to what we did in red here, just that the log base 10 is a common base to use. The reason it's a common base to use is kind of similar to why the log base e is a common base to use. E is the perfect base for exponents in some calculus sense. So because we use that base in exponents so much, it shows up a lot in logs. Similarly, 10 is a nice base when we're dealing with exponents because multiplying 10s together works out so nicely in our base 10 system that 10 also ends up being a pretty common base for logs. Just like we have special notation for the log base e, we have special notation for the log base 10. The way you can write the log base 10 of a million is just by leaving off the base. If you ever see log written without any base at all, it's implied that the base is 10. The idea there being the most common bases are going to be e and 10. So for e, we have this shorthand, natural log, and for 10, well, how about we just leave it off? Just like the most common root you see is the square root. Sometimes you have a cubed root, and sometimes you have a fourth root or a fifth root. But the most common one you've probably seen in your mathematical career is square roots. Note, we don't put a 2 right here. You could put a 2 right here. It might make more sense. It would make it more similar to cubed roots and fourth roots, but you don't. If there's nothing written here, there's an implied 2 on this root. It's the same idea with logs. If there's nothing written in the base, there's an implied 10 there. So if somebody asks you, what's the log of, I don't know, 0.01, really what they're saying is what is the log base 10 of 0.01? And that's not easy to figure out, but if you rewrite this decimal as a fraction, so we can think about it as 0.01 divided by 1, now it's a fraction, and then I don't like having these decimals, so maybe I'll multiply the top and the bottom by 100, that'll move the decimal place 2 spots to the right, and I'll get 1 divided by 100. I can rewrite this question as the log base 10 of 1 over 100. And now it's a little bit easier to figure this out. The log base 10 of 1 over 100 is just asking me what power do I have to raise 10 up to make it equal to 1 over 100. Well, 10 squared is 100, but I don't want 100, I want 1 over 100. So I guess that would be equal to -2. I wasn't really trying to give you more examples here. What I was trying to do is just tell you that if you ever see log written without a base, it means the log base 10. And if you ever see natural log written, it means the log base e. One last comment that I have on the bases for logarithms goes all the way back to the basis for exponential functions. Maybe you remember when we were talking about exponential functions, we said that you can assume that the base b is always greater than 0. And then we kind of studied the case when the base was between 0 and 1 and compared that to the case where b was greater than 1. Well, with logs, when we have logarithmic functions like f of x equals log base b of x, we also have restrictions on the base. And the first restrictions we make kind of follow the ones that we made with exponents. We definitely want the b to be a number that is greater than 0 because it doesn't really make sense to have a negative base here. For the same reason we wanted to keep the base for exponential functions positive. We wanted exponential functions to be defined for all values x. We want logarithmic functions to be defined for as many values of x as possible. And so in order to do that, we at least want to keep b positive. But we're actually going to go a step further. If you think about the log base 1/2 of x, what this is telling you is what power you'd have to raise 1/2 up to make it equal to some given value of x. What I'm saying is this is equivalent to 1/2 to the y value equals x. But rather than figure out the power that we'd have to raise 1/2 up to make it equal to x, what we can do is figure out the power that we'd have to raise 2 up to make it equal to x. It would almost be the same. It would just be the negative of the value you have up here, because the negative would mean take the reciprocal of this. What I'm saying is anything we do with a base of 1/2 can also be done with a base of 2. We would just end up with the negative of whatever the y value is. So since anything we need to do with a log base of 1/2 can be done with a log base of 2, what we typically do, what you'll typically see is the base here will be assumed to be greater than 1. And that's a little bit weird. It's not because there's anything wrong inherently with having a base that's less than 1 as long as it's positive. The log base 1/2 still makes sense. It's just that you don't really need it and it kind of confuses things. So what mathematicians typically do is they assume that the base with their log is greater than 1. In this class, anytime we talk about logarithmic functions, which is what we're going to do for the rest of the chapter, we can always assume here that the base is greater than 1. Even though bases like 1/2 technically make sense, you'll never see them in this class.